Welcome back. So this is our third video about using Bayesian networks as classifiers, and in this lecture we're going to discuss some extensions for the naive Bayes classifier. The general idea behind all those extensions is that we should break this assumption that all attributes are independent between each other given the class. So instead of using this predefined structure, we're going to learn the structure from data. One extension that we're going to look more closely is called the tree-augmented Bayes classifier, or just 10. And this idea of having a tree is that we will learn the graph in each variable has at most one parent. So it's possible to have a structure like this. So we have one parent, and each variable here has just one parent. So this is alouette, but we cannot have two parents pointing to the same node. So the structure we're going to learn is a subset of all DAGs that we could use as a Bayesian networks. And the idea here is to use the conditional mutual information as a measure of dependency between variables. And we're going to link variables that have a very strong dependence between each other given the class. So let me try to explain the tree-augmented Bayes classifier using one example, and I'm going to see the algorithm later. The general idea is to test a pair of variables and measure the conditional mutual information between them. So just to remember the equation I included here, this is how we computed the conditional mutual information, but in a very general way, what we are doing is a weighted average, where we are weighting by this probability here of the log of a ratio. And this ratio is very interesting because this ratio is going to be 1 if the two variables are conditionally independent. Remember that to be conditionally independent, we have this condition here. So the probability of AI and AJ given C is going to be the multiplication of AI given C and AJ given C. So when you have this condition here, we have the conditional independence between the variables, and the ratio is going to be 1. As we are computing the log of the ratio, this is going to be 0. That multiplied by this term here is going to be also 0. So something that's interesting about the conditional mutual information is that it is always greater or equal to 0. So it means that if you have these conditional independences between the two attributes, you're going to be 0 or very close to 0. But as we increase, we are starting measuring the conditional dependencies between the variables. So and this conditional dependency of the variable is exactly what we are interested in the case of naive Bayes, because we are assuming that every pair of variables are independent between each other given the class. But if the conditional mutual information is informing us that is not true, it will be important to link those variables in order to account for those dependencies. And that is the general idea of the algorithm. So here we have a small data set. So we're going to learn the structure from the data set, and afterwards we're going to learn the parameters from the data set too, but that's going to be exactly what we did in the previous video, so we will not cover that again. So we're going to discuss now mostly the learning of the structure. And it's going to be important for us because it's sort of a preview we're going to see in the future lecture when we're going to learn how to learn the structure about the entire Bayesian network. So that's going to be a simpler case for something that we're going to see in the future. So we started the algorithm by taking all the variables. We're not going to include the class, so only the attributes. And we're going to connect those variables using a fully connected undirected graph. So we're going to have like this situation here without the weights yet, because we're going to compute the weights later. So we take all the attributes and connect them in a fully connected undirected graph. And the second step is to compute the weights, and the weights are exactly the conditional multiple information. So the conditional multiple information between A1 and A2 here is 0.85. And it comes from this table here. It is just applying this equation that looks very daunting, very complicated, but you know, we can boil down to some probabilities. So we estimate all those probabilities from this data here and compute the equation. So it's going to be 0.85 here and 0.16 here and so on. So we have to compute this conditional multiple information for every pairs of variables. As we have finished with that, as we are interested in having a graph that connects the variables that have the stronger dependency, we will compute what we call the maximum spanning tree. And we have seen in the tutorial 1 the minimum spanning tree, but the maximum spanning tree is the same thing. We just have to replace the min heap by a max heap, but the algorithm is essentially the same. So this algorithm, you're going to start with one of the attributes like A1. You're going to see all the possibilities that are connecting A1 to all the attributes. You're going to take the maximum one. So you're going to take this guy here. It's going to change. Let me erase this. So the general algorithm is you start with a node. We check all the possibilities. So we have this possibility here, here, and here, and we chose the one with the largest value. So now we have two nodes in our spanning tree. You're going to see all the possibilities that connect these two nodes to all the other nodes that are not selected yet. Okay, so we look at all possible edges that connect A1 and A2 to the nodes A3 and A4. So we're going to also look at this guy here and this guy here. So our possibilities are this 0.9, this 0.8, this 0.16, and this 0.16. And we had to take the largest one, and the largest one is 0.16. So we have a tie here, and it means that we can have more than one maximum spanning tree, and that is normal. It happens frequently every time that we have those ties. So we're going to take this edge here. I'm going to include A4 to this maximum spanning tree. And now the maximum spanning tree has A1, A2, and A4. And we're going to look at the edges that connect these three nodes to A3. And we have three possibilities. One is, again, 0.09. Another possibility is 0.08 here. And we have another possibility that is 0.21. And the largest one is going to be 0.21. So we're going to use this edge and connect to A3. And now we have the maximum spanning tree as we are illustrating in this part of the figure here. Okay, so now we have an undirected graph and we need to choose the directions. And unfortunately, it would be very nice if we could identify the causal relationship between the variables, so we could point them in a causal direction. But unfortunately, that is not easy to measure because this is associated with some semantics, some meaning that we cannot grasp that directly with probabilities. So what people usually do is to select one node as root, so it's going to be like A1, and direct the edges outward from the root. So we're going to point the edge this way. Again, going to point this way and going to point this way. Right? So it's one way of giving directions to the edges. So, and the final step is to include the class attribute and make one edge from the class attribute to each attribute. So if you see here, we have exactly this in the last figure. So we have A1 here that's pointing to A2, is lastly as we have here. We have A2 pointing to A4 as we have here, and we have A4 pointing to A3. And we add the class attribute and make the class attribute point to each of the attributes that we have. So in some sense, we have a naive Bayes classifier. So we have a structure that remembers the naive Bayes classifier. That is the flat structure that we have the class in the top and all attributes in the bottom. But now the structure is not completely flat because we have some edges between the attributes, and those edges are accounting for the dependencies that we have between them. So let's take a look on the next slide and see what this dataset means, and if it matches our intuition between dependencies of variables. So this dataset here is a little bit special. I created that in order to illustrate the algorithm. So there are two ways of find out the value of the class. The class can be the XOR of A1 and A2, and the class is also at the same time the AND of A3 and A4. So if you look here at the data set, we see that every time that A1 and A2 are equal, we'll have a negation here, so it's not being the class is going to be false. Here they are different, and the class is true, and again different and true, and again different and true, and now equal and false, exactly as it is defined for the XOR. At the same time, the class is also a conjunction of A3 and A4. So here we have false and true is going to be false, and have true and true going to be true, true and true, true, true and true, true, true and false going to be false, and so on. So a class is at the same time the XOR of A1 and A2 and the AND of A3 and A4. And why I did it this way? Because the XOR is a little bit special. We cannot figure out the value of the class by just looking at one of the attributes of the XOR. If you look just at A1, it will not be enough, right? Look at that. We have here A1 and false. We have here A1 and true. We have here again A1 and true. We have not A1 and true. So it's not enough to look at just one attribute. And it's going to happen also to A2, because XOR is only meaningful when you look at the two attributes at the same time, because they need to be equal or different. So that is the information that we need to figure out. So in this case, A1 and A2, they are highly dependent of each other in order to figure out what is going to be the value of the class. For the AND, it's the two attributes, they are dependent, but the dependency is weaker, because sometimes just look at one attribute is going to be enough to figure out the class. So when one of the attributes is false, it's guaranteed that the class is going to be false. So as we have here, as we have here, as we have here. When the attribute is true, well, we have to look at the order one. So part of the time, A3 is going to be enough to figure out the class. Another part of the time, it will not be enough. So the dependency is not as strong as in the case of XOR, but it still is some dependency. So if we look here, our final three augmented Bayes classifier, we figure out that A1 and A2, they have a very strong dependency. So we have this value that is very high. A4 and A3, they have some dependency. It's not as strong as this one, but it's still a significant number, right? So it's larger than this one that is just spurious, because, well, we do not expect it to have a strong dependence between A2 and A4. Okay, so it seems that these three augmented Bayes classifiers is doing what is proposed to do. So what we have to do now is to compute the chain rule for the Bayesian network, and so you have the factorization, and you use this to compute the empirical probability. So we have here P of C, and is correct because C has no parent. We have A1 given C. We have A1 here given its parent, single parent C. We have A2 given, so A2 is here, given A1, that's here, and C. So A2 has 2 parents. So we may ask now, well, we didn't say that it's going to be a tree instead of a general DAG, but now we defined the tree as the nodes having a single parent, but now we have A2 having 2 parents. How is that possible? So the tree is this part here, right? As we added later the class attribute and pointed the class attribute to all the remaining attributes, that's not going to be a tree anymore. But the tree is only the part that we computed using all the attributes in the previous slide. So we have A3 given A4 and C. We have A3 here in the edge, 2 parents, A4 and C, that's correct. And then we have A4 given the 2 parents A2 and C. So that's correct. So now we have the factorization. We can compute and estimate these empirical conditional probabilities and use this to classify the data. Let's take a look in the next slide. So here we have the algorithm. So we compute the conditional multi information for every pair of variables, and next line we create a graph G that's a complete underwritten graph over all the attributes, not include the class, with the weight M, and M is exactly the conditional multi information between these 2 attributes. So we compute GT, and T is for the tree, it's a maximum spanning tree for G. And now is the time of choosing one variable as the root and setting the direction of the edges, because they all indirect edges. We need to convert them to direct edges. So we chose one variable as a root and set the direction of the edges outwards from the root. And the next step, we added the class attribute and create one edge from the class attribute to each attribute, and we will learn the parameters given the factorization created by this structure, and return this. So it's the classifier. So there are other 2 extensions of the naive Bayes classifier that are also very well known and used in practice. One is called the Bayesian network augmented naive Bayes, and the other one is called the general Bayesian network. So they are very similar to the tree augmented that we saw, but instead of learning this tree structure, we're going to learn a DAG structure. For the Bayes classifier, we're going to learn this DAG using only the attributes, and we're going to add the class attribute later on and point edges from the class attribute to every attribute, pretty much like we did with the 10. For the GBN, it's going to be slightly different. We're going to learn this DAG structure using all attributes, including the class attribute. And I'm going to compute the Markov blanket and use only the variables inside the Markov blanket to make the classifications. So very similar to what we did in the first part of this lecture. Okay, so we're going to see how these algorithms for learning a structure from data, they work in a future class of this course. But just to mention that this idea of learning a tree structure from data using the maximum spanning tree is known as the Chow-Liu algorithm. So it's a very famous algorithm. It is also used to learn Bayesian networks using tree structure, but in the case of Bayesian networks, we only use the multi information. We don't use the conditional multi information. The conditional multi information is more relevant to the problems of classification, where we condition everything to the class. So it may be interesting to look at some experimental results for this. And there is one paper here that made the experimental comparison and included a few UCI datasets. So these are classical benchmark datasets, and the idea was to compare these 4 classifiers using these 8 UCI datasets in order to have a little bit of understanding how they can improve the classification over the naive Bayes classifier. So we can see here, so this is the naive Bayes classifier, and we can see that overall the 10 can increase a little bit the accuracy of those classifiers. So we can see like in 84 to 86, you have 90 to 91, you have 95 to 99, we have 87 increasing to 92, and so on. So we see that there is a little bit of a gain in terms of accuracy when we account for the dependency between the variables. Here we have the band, and the band and 10 are very similar, but the band learns a DAG structure instead of the tree structure. And we can see that there is some minor improvement too. So yeah, sometimes you also lose a little bit of accuracy. So here we have a reduction of accuracy, but here we have a little bit of improvement, a little bit of improvement, and so on. So we can see that sometimes for some data sets, we can have a little bit of a gain when you move from 10 to band, but it seems to me that the improvement from the naive-based classifiers to 10 was more significant. And here we have the full Bayesian network that we're learning from data, and reminds that this structure that was learning from data is not an expert that gave to us. So something that's interesting to look at the general, what's called the general Bayesian network here, is the fact that it is doing a little bit of feature selection. So we are not using all the features, we are using a subset that are the features that belong to the Markov blanket of the class attribute. So here it's showing that we are using 8 features in 13. So the data set has 13 features. We are using 8 to compute the classification. Here we are using 6 in 8, 5 in 22, and so on. So the authors included this information also for us. And the performance of the GBN is not bad compared with the naive-based classifiers. There are some significant gains here. Okay, so we got to the end of this lecture, and we saw how we can use Bayesian networks and derivations to solve classification problems. We saw that classification is a task that matches the map and MP queries of the Bayesian networks. We saw that we can naturally deal with Bayesian networks when we have a missing data into the test cases, and we're going to see in a future class when we study how to learn the parameters from data that we can also naturally deal with missing data in the training set as well. We saw that when you're dealing with complete data and working with Bayesian networks, not all variables will influence the decision for the class. It's going to be a subset of those variables. And if you look at what are the probabilities that are used, you're going to see that it's an even smaller number. So just the probability of the nodes in which we have the class attribute. We saw review the naive-based classifier, very popular in certain areas such as text mining, and it has a fixed structure, but we can change that if we are willing to learn the structure from data, and some extensions do exactly that. When you learn the structure from data, it opens the possibility of having edges between attributes that are strongly dependent between each other. So we're going to break the classical assumption of the naive-based classifiers that all attributes are independent of each other given the class. Great, so this lecture is going to be the basis for our first assignment. So I invite you to take a look in the assignment description and think a little bit how to solve that, and if necessary, review the content of this lecture. In the next lecture, we're going to start discussing the variable elimination. That is a very well-known popular algorithm for inference in Bayesian networks. See you.